Modern jet engines operate under thermodynamic conditions that exceed the physical limits of their own structural materials. Turbine inlet temperatures in advanced propulsion systems now reach 1600 to 1650 degrees Celsius. This is up to 300 degrees hotter than the melting point of the single-crystal nickel-based superalloys used to cast the turbine blades. To survive, these blades rely on a microscopic ceramic shield. A layer of yttrium-stabilized zirconia, just 100 to 250 micrometers thick, must drop the temperature by up to 300 degrees. This thin barrier is the only thing preventing immediate structural failure. If this coating fails, the consequences are instantaneous. Ingestion of environmental dust or localized cracking causes the ceramic to flake off. Exposed to raw combustion gas, the underlying superalloy melts within seconds, destroying the engine. The supply chain for this critical ceramic is highly concentrated and geopolitically vulnerable. Refining raw zircon sand into aerospace-grade zirconia requires reducing hafnium impurities to under 100 parts per million. China controls 58% of this specialized purification capacity. The primary Western alternative is Saint-Gobain in France, which holds a 22% market share. This leaves Western defense and commercial aerospace manufacturers highly exposed to unilateral export restrictions on precursor materials. The vulnerability is even more acute for the stabilizing agent, yttrium oxide. This heavy rare earth element is essential to prevent the zirconia from undergoing catastrophic phase changes during thermal cycling. China controls over 85% of global yttrium separation and refining capacity, creating an absolute single point of failure. Even if raw material supplies are secured, the physical capacity to apply these coatings is severely constrained. The industry standard for depositing high durability, columnar ceramic structures is electron beam physical vapor deposition. The machinery required is highly complex, expensive, and produced by only a few specialized German firms. Lead times for these multi-million-dollar coating systems have nearly tripled, rising from 12 months in 2018 to over 32 months in 2024. This delay is driven by a global manufacturing bottleneck at firms like ALD Vacuum Technologies and Von Ardenne. The active global order backlog has reached a record 41 units. This surge is driven by simultaneous production ramp-ups for commercial engines like the LEAP and advanced military propulsion programs. The physical limit of high-vacuum engineering is now directly pacing the deployment of next-generation aviation hardware.